two different states, because here these third neighbors are always paramagnetic, while here they are antiparamagnetic. So there are some competing interactions. In order to see this, we just plot all these interactions. R here is the same X, so it's just changing the notation. But in any case, what is important that in the vicinity of the Kitaev point, the largest interaction is this kind of flux interaction, this third interaction. While first interaction coming only from K2 coupling is dominating in the biggest part of the phase diagram, and it competes with with a J2 interaction only in the vicinity of the Kitaev spin. So it's the question: is there three phases, or there are just two magnetic phases in each of the quadrants? Okay, so Ioannis did exact diagonalization, because from perturbation expansion we could not make a decision what we will get. Both cases were possible, but in the exact diagonalization studies, which were done on the 32-side lattice and 34-side lattice, only one type of phase disappears. So basically, J1 type of effective coupling always weak. So this is the quantum phase diagram of K1, K2 model, and what we see that quantum spin liquid state in the vicinity of positive K1 and negative K1 is extremely fragile with respect to K2 interaction. And therefore, I think one of the reasons why sodium iridate is in the ordered phase, and it's probably deep in the ordered phase, is because K2 interaction is rather big, so it's probably quite far from quantum spin liquid. It's interesting phase diagram because each of the magnetic regions actually contain 12 degenerate quantum states. So these the states which I show here is only with spin pointing along the axis, but you see that there are two different spins. Here there are two different spin structures for each quadrant, and they have completely different structure factors. So then these two should be multiplied by 2 due to time reversal, and it should be multiplied by 3 due to for the substitution of x, z to x and y. So each quadrant has 12 states, and if that model would be realized, then it would be very non-trivial how to basically analyze the spin wave data or some Newton scattering data. It would be a possibility to have this particular model realized in nature. Okay, so another important thing is that these states are very Ising-like, and basically you can see it here where it's the square root of the structure factor. Here both result from exact diagonalization and from nonlinear spin wave expansion. So you can see that the structure factor is very close. So in the magnetically ordered phases, it's very close to 1/2. So the spins are basically almost Ising, despite the fact that the nature of the ordered state is purely quantum. And one can also see that spin wave, even nonlinear, so it's the result of taking 1/s expansion is actually not really sensitive to Kitaev spin liquid, because it's one of the states, so it basically does not show that the spin length is going down in the spin liquid phase. And here is another result from exact diagonalization. So this is the expectation of the flux operator in the ground state obtained by exact diagonalization. And one can see that as it should be in the Kitaev spin liquid, so for K2 equals 0, the expectation value of the flux operator is 1, and basically it's going to almost 0, so it's just very small number in the ordered phase. So the difference from 0 is due to finite size effect. So triangular points was considered before, and basically in our model that corresponds to K1 equals 0, in which case we will have two triangular suborbitals which are not talking to each other. So the first work about triangular points was once again by Ioannis and other people, and Maria de Goffer is here. And basically they looked to the classical K1 Kitaev model, Kitaev-Heisenberg model on the triangular lattice, and they saw the same type of nematic state as we saw in K1, K2 model. And the quantum Kitaev model on the triangular lattice was considered, as I already said, by George, and basically it was the same type of processes which leads to the ordering. And then it was also some analytical and numerical works related to this study. Maria Herman is also here. Okay, so here's my conclusion. I talk about K1, K2 model. I think it's an interesting model because it holds a number of unconventional aspects. There's not so many models which we know that which has completely different thermal and quantum fluctuations. Then it's important that magnetic long-range order in this model can be stabilized only for quantum spin and not for classical spin. And the reason for this is the symmetry, the sliding symmetry of the Hamiltonian. Despite the fact that this ordered state, quantum state has very Ising character. And the classical spin can have only nematic order at finite temperature, and it would be very interesting also to study quantum K1, K2 model at finite temperature, but due to sign problem, Monte Carlo is kind of complicated, so one needs some tricks how to study it. And I really believe that K2 interaction is relevant at least for sodium iridate, because for this compound, as we got, K2 is the largest energy scale after nearest neighbor Kitaev interaction. And since the Kitaev spin liquid is significantly more fragile against K2 interaction than against Heisenberg interaction, then probably that demonstrates that sodium iridate is a bit inside the magnetically ordered phase. And if somebody wants to get spin liquid, one of the things to be checked is that K2 is small. Thank you very much for your attention.
I have a few small clarifications. So, your G21 effective engineering, they are not isotropic shapes.
Oh, they are Ising coupled. They are simply Ising coupled.
Start with the picture of classical
we did for spin 1 half. We did for spin 1 half. Yes. So you mean this process? Yes, we did it. It's just a perturbation theory, basically, nothing else. So you have a degenerate ground state, you choose one. Basically, you assume that decoupling is larger in order to stabilize this state.
ほとんどみんなそのつもりでいるの。みんな覚悟してたよね。
I just think so. Whenever we computers we take on the second part, then we just take the expectation value of product of sigma sigma. Yeah, it's for spin 1 half. So these values are taken by spin 1 half, and basically these number like 4 and so on, that's coming by the multiplication of 1 half.
Out of the decrease the value of the spin, and it may change the uniformity function.
It will go to zero. So as spin is going, if spin become more and more classical, all these couplings will go to zero. And basically when we are talking about classical spin with infinity, they will be exactly zero. And that's related to the
Maybe just because the effective spin will be
Sure. I mean, but then it should be still large but quantum spin because we need the quantum nature of the spin. We need the commutation relation.
その思いをね理解して。